All right, we're going to go ahead and begin. So, hello everyone, and on behalf of the Environmental Finance Center Network, welcome to another session in our Operator Certification webinar series on loading, removal, and BOD math. My name is Avery Davis from the Syracuse University Environmental Finance Center. And before we begin, we're going to cover a few housekeeping items and then we'll get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We'll be saving your questions for a Q&A session at the end of the presentation. After the webinar, you will all receive a follow-up email that includes a link to the recording and other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. Webinar has not been submitted for pre-approval of continuing education credit, but eligible attendees will receive a certificate of attendance for their personal record. So in order to receive a certificate for this session, we ask that you attend the entire webinar and register and attend individually using your real name and unique email address. We do not accept group viewing credit. Certificates will be sent via email within 30 days of the webinar date. And if you have any questions or need assistance, you can contact us at smallsystems@syr.edu. Now for a little bit about the Environmental Finance Center Network. We provide training and technical assistance to small water and wastewater systems in all U.S. states and territories. And if your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing a link for shortly in the chat. And on that note, I would like to introduce our presenter for today. So we have AJ Barney, who is a research scientist at the Southwest Environmental Finance Center. So AJ, welcome, and I hand everything over to you.
Thank you, I appreciate it. Like she said, my name is AJ. I'm a research engineer at the Southwest Environmental Finance Center. I've worked in wastewater for about 10 years. I'm a level 4 wastewater operator in the state of New Mexico. I've worked in operations at the wastewater plant in Albuquerque, as well as compliance and supervisory roles. And then now I moved over here after completing my civil engineering degree. So I would like to take this opportunity real quick to promote a new Environmental Finance Center Network program available to small communities. So the Southwest Environmental Finance Center is currently offering new technical assistance opportunities covering aspects of wastewater pretreatment. If your community or municipality or your system is in need of assistance with their FOG program, implementing your EPA dental rule, industrial sampling, or any other aspects typically covered by pretreatment programs, we would be delighted if you would contact us and see if we can provide you any assistance. My email is right there if you want to, if you're interested in that, and you can also fill out the form on the Environmental Finance Center Network website. Also, we would like to mention that we are currently working on offering weekly wastewater technical assistance office hours. So this can cover stuff like troubleshooting, operator certification, training, financials, FOG, and other pretreatment topics. And we are going to be doing this through the Southwest Environmental Finance Center Zoom channel. And this will be every Tuesday from 11 a.m. to 12 p.m. So it's just gonna be an hour Mountain Standard Time. If this becomes popular, we're interested in doing more of these, and we can be flexible as well if you need some help. So you can contact us either through email, you can contact me or James, and or you can also leave your email in the chat if you'd be interested in participating. So a little bit about operator certification. These are typically overseen by state environmental departments. Some examples are from the EPA Region 6 or the Texas Commission of Environmental Quality, the New Mexico Environmental Department, and the Oklahoma Department of Environmental Quality. There's also EPA operator certification, which is designed to have reciprocity with your state levels and is utilized by communities such as tribes. Each of these agencies has their own level hierarchy based on the different criteria the certification may serve, such as the complexity of the system, the population size the certification can cover, and years of experience required to operate the plant. There are various resources each of your states offers, such as need to know criteria for the exams, study guides, and then there's also the California State University of Sacramento Wastewater Operations Manual, which is kind of like the go-to for many systems and operators. So it's important to become familiar with the resources that you're provided by your state and that are available to you, because this training typically is a good resource and a good overview, but we always can't go into like the details that you might find on your test. We try to, for this one, we go into a lot of the math, but typically it's needed that you need to put a lot of time and dedication to get your certification levels. And in saying that, we'll go ahead and start our webinar. So a quick overview, we're going to do a quick math review. I'm going to just mention some of the topics that we've covered in other webinars, as well as videos that we have available on the Environmental Finance Center Network website. And then today we're going to talk about loading and the different types of loading that you're going to see on wastewater operator certifications, as well as in the field and in the real world. Then we're going to talk about removal efficiency, and then also just a little more details about biochemical oxygen demand and some of the math that might apply to that. So real quick on the math review. So it's important to understand some of the concepts of area and volume that you might see. And so a typical surface area is going to be either your circle or your square or rectangle formulas. So for a circle, I like the pi r squared formula, but a lot of people prefer the diameter because it's typically what's provided. So for both of those, it's either pi r squared, which is r is equal to your radius, and then the second one, pi d squared over 4 is your diameter, and your radius is just half of your diameter, which I'm sure a lot of you already know. And then for the area for a square or rectangle is going to be your length times your width. And then for volume, it's both of those problems just multiplied by the height. And you can see that in the equations right there in the middle where it says volume. Some other concepts are going to be concentration, which is typically the mass of a constituent over the volume of water that it's in. And this can be measured in milligrams per liter, which is also equal to 1 part per million. And then also 10,000 milligrams per liter is equal to 1%. Those are important concepts to remember when you're doing these types of problems. Then the final one that I want to mention is flow, which is typically going to be the volume of water over time that passes through a particular point. And this is typically measured in like gallons per day, millions of gallons a day, it can be cubic feet per second, or it can even be in like SI units, the metric system. And it can also be measured in velocity times area. The other part of the math review that I want to mention is kind of the strategy for word problems. So the first thing that we always want to do is identify what's given in our problem, and then also what we're trying to find. We want to recognize the values for what's given and also the units. So after we do that, we can identify our needed equations. A lot of times the way that we find our needed equation is by identifying what we're trying to find, and then also our unit conversions. And you'll try to identify what's given versus what's in the equation and what needs to come out at the end, and try to match those up with your unit conversions. Then the next step would be to set up your equations and rearrange them if needed. So you might need to use a little arithmetic to multiply both sides by a certain term to make sure that they equal what you need. And then you're going to go ahead and plug in your givens. After that, when your equation is all set up, you go ahead and cancel the units and solve. And then you check your answers and decide if the answer makes sense. A lot of times that might be from previous knowledge of what you've seen before, or what you know as are typically the given design parameters. Okay, so the first topic we're going to talk about is wastewater loading. Loading is the measurement of the amount of a given constituent, which I like to just designate as X, introduced to a system over time. So the most basic way to explain that, or to represent that as just the loading rate for that X compound, and it's going to be pounds of it per day. And the way that we calculate that is multiplying the concentration times the flow times our unit conversion, which is 8.34 pounds per gallon. If you guys have been with us in previous webinars, you'll recognize that from our chlorine dosage a couple weeks ago. And when we talk about loading in wastewater, it's typically the amount of the nutrient and contaminant per pounds per day, but it can also be like kilograms per day if you're using SI. And this will apply to such things as like BOD, COD, different chemicals. It can be solids, dissolved solids, total solids. So there's lots of different stuff that this can be involved in. And that's where we would use that. So we're just going to jump straight into a sample problem, and I'm going to walk you guys through this. So a typical sample problem, what you might see is, I'm going to read the problem first, and then I'll kind of discuss the parts of it. So you work at a wastewater treatment plant with a 900,000 gallon a day flow. You perform a total solids test by drawing a sample of the flow and find that the total solids concentration is 1,014 milligrams per liter. On average, they consider 1,000 milligrams per liter, so this is very close to that, so this would make sense. And it was the approximate total suspended solids loading of this wastewater if total suspended solids makes up approximately 20% of the sample. This might be important because this might give you how much solids you want to remove from like a primary clarifier, and you would know how much treatment or solids handling you would need. So again, I left the equation just up there so we can take a look at that. We can already think about what, so we're going to run through our strategy for the problem. So again, the first part is to identify the givens and what we're trying to find. So I highlighted the givens. So the first one is at 900,000 gallons a day. And then we also identify that there's 1,014 milligrams per liter. And then what we're trying to find is the loading rate. So we asked, what is the approximate TSS loading for this plant if the TDS makes up approximately 20% of the sample. So we know that total solids is our concentration that we're going to be using for the problem, but we really need 20% of it for our total. Oh, I'm sorry, I don't know why it says TS. That should be TSS. Sorry about that. But right here in the formula and in the word problem it says TDS twice, but that should be TSS. So we know our flow, we know our concentration, and we already have our unit conversion. So we're going to go ahead and start setting up the problem. So what we do is we first need to figure out what 20% is going to mean to our problem. And so the way we do that is we divide 20% by 100%, and that equals 0.2. So we know that the concentration for our TSS, and yeah, I wrote TDS, but that should be TSS, my apologies. That should be 0.2 of the total solids. We also know that our flow is given in gallons a day of 900,000. So to convert that, we use a unit conversion of there is 1 million gallons per million gallon, and that 1 million gallons will go on the bottom term of our, or the bottom part of our second term, and the million gallons will go on the top, and so that results in 0.9 milligrams per day, or million gallons per day. And then we set it up in the equation, and we're going to go ahead and just plug it straight in and do it horizontally. So then our next step is to cancel the units. So we remember that, if you guys remember that, a milligram per liter is equal to a part per million, which can be represented as 1 over 10 to the 6th or 1 over big M. I put it in the equation as 1 over 10 to the 6th because typically M in this type of chemistry or wastewater chemistry might be confused with molarity. So I like to just represent it as numerically. So that 10 to the 6th cancels out with the M in the 0.9 mgd, and then the G is gallons, and that cancels out with the gallons on the third term. And if we multiply straight across, we get 6,088.9 pounds per day of TSS loading. and give it based on our concentration. This is a reasonable answer and our units make sense. So we'll go ahead and decide that this would be a good answer for us. So now, since we've done the sample problem, I'm going to introduce a practice problem to you guys, and that's going to be our first poll question. So if everyone wants to get out a piece of paper and a pen, or whatever you usually like to use, here is the question. So the practice problem is going to be the mercury limit for most wastewater treatment plants is 0.008 micrograms per liter. So we're going to keep that in mind when we see that a different unit than what we're used to, and understand if we have a conversion factor. And we would like to limit loading into the river that the wastewater treatment plant discharges to 0.001 pounds per day, which is pretty reasonable because mercury is highly toxic and causes lots of problems with reproduction and wildlife. So we want to keep it on a nice low limit. So in order to achieve that, what is the maximum flow allowed to achieve this goal if the plant is at its mercury limit every day? So what we have is we have the equation right here, and I gave you a conversion factor for the micrograms. And then this problem does require a little bit of arithmetic rearranging. And I'm going to go ahead and give you guys a couple minutes to look at it here, and then we'll go and throw up the poll question once you guys kind of have the answers ready. Okay, Avery, if you want to go and throw up the poll question. So based on the equation that we did, what's the maximum flow allowed to achieve this goal if the plant is at its mercury limit every day? And the answers are 10 feet per second, 15 gallons per day, 15 million gallons a day, or 10 million gallons a day.
Right, it looks like about 45% have answered. So I'm gonna leave it up for a few more seconds, but just know if you get this answer incorrect, you will not be penalized. It's just for your own practice. So get those answers in. I'm gonna close the poll in 3, 2, 1. And there are your results, AJ.
All right, so it looks like the majority of us who answered did get it correct. Or I guess we got more right answers than any of the others. So the right answer was 15 million gallons a day. And if we want to go ahead and move on from the poll, I'll go ahead and walk you through the answer. So the first thing we gotta do is identify our givens. So we have 0.008 micrograms per liter, and then the loading that we want to achieve is 0.001 pounds per day. So that means that we have to rearrange our previous question. So if we divide both sides by the concentration and the unit conversion, we get our flow is equal to our mercury loading over that concentration and the unit conversion. Now, the first thing we need to do is after that is to convert our micrograms to milligrams. And so we use a conversion here where we multiply by 1 milligram over 1,000 micrograms, and that results in 0.000008 milligrams. And when we plug that into our equation, so first our loading goes on the top, and then on the bottom, you'll notice that the number looks a little odd. It's 0.000008 times 1 to the 10 to the 6th. What that is that's making it equal to our part per million. So we have per million on the bottom, and then we have our unit. So the pounds cancels out. Now, if we have per million and per gallon on the bottom of a fraction, when it is moved to the top, it becomes the top. It becomes the denominator. And so that's why we get 50, that's why our new units are million gallons per day. And if we just solve this and we divide 0.001 by 0.000008 and 8.34, we get 14.9 or approximately 15 million gallons a day because we've rounded that up. All right, so another type of loading is going to be surface loading rates. And this is applied to primary and secondary clarifiers, as well as like a trickling filter clarifier. And it's related to the settable solids removed efficiency of a settling tank. And basically shows you how much, based on the area of a clarifier, how many solids it can handle based on the flow that's coming in. So you can see that the efficiencies for primary and secondary clarifiers are typically between 300 and 1,200 gallons per day per square foot. And then trickling filter is a little bit higher, well, the minimum's higher, and that's because it needs to be able to handle sloughing or more solids. And it's just typically not going to be seen as low as the other types of clarifiers. And also the lower rates for a surface loading rate will result in longer detention times and can lead to problems associated with that, such as going septic or solids starting to settle too quick, or like they don't. Yeah, basically just it's issues with septic. Then you can get some floating solids from that. So some of these questions, we're just gonna give you the equation and we're just gonna practice solving them. So it's just gonna be like the last problem. I'm just gonna give you the practice problem because these are pretty straightforward, and I'll give you the associated equations, and then we'll go ahead and practice them real quick, and then I'll walk everyone through the answers. So we have about 3 or 4 of these that are gonna go pretty quickly like this. So the first problem for the surface loading rate, this is going to be a primary clarifier, has a diameter of 42 feet, and has a flow of 1.1 mgd. Now the question is, what is the surface loading rate of this clarifier? So we'll give you guys about 2 or 3 minutes to work on this, and then we'll throw up the poll. All right, let's go ahead and put up the poll question and see how everyone's doing on these. This one, as you can see, these numbers are pretty round, so you guys are probably going to get a number that you need to round up or down.
About 45% who have responded. So I'm going to close the poll in just a couple seconds. So get those answers in. Close the poll in 3, 2, 1. There are the results.
All right, so it looks like everyone did really well on this one. That is the correct answer, 719 gallons per day per square foot. If you'll notice, the first answer is in million gallons per day. So we know right away that one's not it because of the units. But let's go ahead and I'll go ahead and show the solution now. So the first thing that we have to do is to find our surface area. And so that's pretty straightforward. We just plug that into our surface area equation, which is going to be pi times 42 feet squared. And we divide that by 4, which results in 1,385.4 feet squared. We plug that into our surface loading rate equation. And then we need our flow, but it was given in million gallons per day. So 1.1 million gallons per day is equal to 1,100,000 gallons per day. So we plug that in as well. Then we just solve and we get 794 gallons per day. All right, so our next concept is going to be similar to our other one. This is going to be our Weir overflow rate. And again, we're going to have a practice problem right after this slide. So the Weir overflow rate indicates the relationship between the flow that a clarifier is designed for and the length of its weir. And it's important to prevent short circuiting. So the length of the weir will be equal to the circumference of the clarifier. That's important to remember. And this may be either given directly in a problem or by the manufacturer if calculating this in the real world. But it's often required to calculate this based on the diameter or radius of the clarifier for testing purposes. Typical overflow rates that you'll see for clarifiers are between 10,000 and 20,000 gallons per day per foot. And the way that we calculate that is dividing the flow by the linear feet of our clarifier. And that, like I said earlier, is the circumference. So now we're going to throw up a practice problem, and we'll just have everyone work on that, and then I'll walk you guys through it. Again, this one's pretty straightforward. So we're going to go ahead and let you guys do it on your own. So the question is, what is the Weir overflow rate of the clarifier from the previous practice problem with a 1.1 mgd flow and a diameter of 42 feet? So we'll go ahead and let you guys solve this for about a minute or two, and then we'll throw up the poll. All right, let's go ahead and see if we can get the problem, throw the poll positions or poll question and see how everyone does. So again, the question is, what is the Weir overflow rate of the clarifier if the flow is 1.1 mgd and has a diameter of 42 feet? And the answers given are 8,400 gallons per day per foot, 10 gallons per day per foot, 84,000 gallons per day per foot, or 8,400 gallons per day per foot squared.
And go ahead and close the poll in 3, 2, 1.
All right, so it looks like most of us got it right again. So the answer is 8,400 gallons per day per foot. If you'll notice the last answer, it's the same numerical value, but it's gallons per day per foot squared. So when you guys put foot square, this should be in feet. So we would, and that's because our circumference is just diameter in feet times pi. So we're not multiplying it by feet again. And I'll go ahead and show, walking us through the answer real quick. So again, we had to convert our flow to gallons per day. We just convert that to 1,100,000 gallons per day. And our circumference is going to be 42 feet times pi, which results in about 131.9 feet. And when we plug that into our equation, we get 8,337 gallons per day per foot. Now, sometimes these tests are not completely accurate, and they might round, a little too far up in that kind of case. But the 8,400 gallons per day per foot was the closest answer. So next, we're going to move on to some solid loading. So this is typically the amount of solids removed by a clarifier. When a flow comes into a clarifier, it's typically remove, I believe, 95 to 99% of settleable solids, or I think it's not like 90% suspended solids. And so this is going to be a calculation of how much of those suspended solids can be removed. The equation is pretty straightforward. It's going to be our solids loading rate is going to be equal to the solids applied per day. And if you'll notice, that equation is below it, and that's a typical loading equation that we did earlier and in previous webinars with like chlorine, but this is one that we did with our total suspended solids as well as the mercury. But it's just a straightforward loading equation for suspended solids. And then we divide that solids applied from our solids loading rate by the surface area of our clarifier. So again, we're just going to introduce a practice problem, and we're going to let you guys solve it. And then I'll go ahead and walk you through how to do it, because again, this is a pretty straightforward one. So a secondary clarifier, also with a diameter of 42 feet and a flow of, that should be 1.1 mgd. That's how I solved it in the thing, but I must have left that decimal off, so apologies for that. But it has a MLSS concentration, which is mixed liquor suspended solids, concentration of 40,000 milligrams per liter. I'm sorry, 4,000 milligrams per liter. And the question asks, what is the solid loading rate of this clarifier? You don't need to do anything special with that MLSS. That's just going to be the same thing as your suspended solids. And again, this should be 1.1 MGD, and that's how you're going to see it solved on the next slide. So use that for the given flow. So we're going to go ahead and let you guys solve this, and then we'll throw up the poll in about 2 minutes or so. All right, if we want to bring the poll question up, we can start seeing how everyone did on this. So again, the question is, we have a secondary clarifier with a diameter of 42 feet and a flow of 1.1 million gallons a day, and an MLSS concentration of 4,000 milligrams per liter. So what is the solids loading rate? And the answers are 26.5 pounds per day per square foot, 0.5 pounds per day per square foot, 26.5 MGD, 790 gallons per day per square foot.
It's like about 50% have voted. Don't see that number increasing much, so please get those answers in. Okay, I'm gonna go ahead and close the poll in 3, 2, 1.
Okay, so it looks like a majority of us got it correct. The answer is 26.5 pounds per day per square foot. So I'm glad my typo of 1 million didn't throw us off. I'll go ahead and walk you through the problem now. So this one's pretty straightforward. The first thing we do is solve for our solids applied. And like we said, this is just a straightforward loading problem where we plug in the 1.1 MGD, the 4,000 milligrams per liter, and then our 8.34 pounds per gallon unit conversion. The million cancels out with the milligrams per liter, because like we said, that's parts per million, the milligram per liter is, and then the gallons cancels out with the gallons, and we just get 3,696 pounds a day. Our surface area was the same as our previous problem, which was 1,385.4 feet square. So we just divide that load, the solids applied by our surface area, and we get 26.5 pounds per day per square foot. So now I'm going to talk about some other loading, BOD loading, which is our biochemical oxygen demand. And we will talk about more into depth about BOD a little bit later in this presentation. So there's a variety of equations for organics loading. And the first one is going to be for trickling filters. And this one requires that you divide the BOD applied over the surface area, which is exactly the same as we just did for our solids loading for a clarifier. But instead of solids applied, this one is BOD applied. And we find BOD the same way we do as the previous problem. And we plug in our BOD concentration multiplied times the flow and our unit conversion. We also have organics loading for a rotating biological contactor, or an RBC. This is typically going to be your soluble BOD applied. So it's going to be your soluble BOD is going to be your total BOD minus your suspended solids times a K factor, or K value, which is usually the value of suspended BOD to suspended solids. So it's a way to guesstimate how much BOD is suspended as opposed to what like the total BOD that gives us our soluble BOD. The K value is typically 0.5 to 0.7 in this type of problem for a certification exam would be given. So after you calculate your soluble BOD, you just divide that by your surface area, and that gives you your organic loading for a rotating biological contactor. And your surface area will be the surface area available on that rotating, that RBC for contact. Next, we have organic loading that you might see for activated sludge. This problem, like you can see, the organics loading is typically what you'll see just for a normal loading problem. You're just going to multiply the flow times the BOD times the unit conversion. But the BOD is what you might find from the effluent of a primary clarifier. So you would calculate this based on the BOD that is measured out of after primary clarification. Also for ponds, you might see the same type of equation where you're going to see the loading on the top, and then that's just divided by the surface area of the pond in acres. Okay, so next we have removal efficiency. And removal efficiency typically shows how effective a process is at removing a desired constituent. It's a good performance indicator, and it can be the value they get from your removal efficiency can be compared to the design parameters or industry standards for the same type of processes to establish if they are working correctly and efficiently. So here are a couple typical plant removal efficiencies. This is overall for a wastewater treatment plant that typically you'd see for like activated sludge. Usually go from 200 milligrams of BOD to less than 30, which is part of the 30-45 rule for both BOD and TSS, which indicates that typical 7-day average should be 30 milligrams per liter in the effluent, and then 45 for a 30-day average. Or I'm sorry, I got that backwards. 30 milligrams per liter is your 30-day average, and 45 can be the max for a 7-day average. Sorry about that. And then for settable solids, you might see 10,000 milliliters per liter come in, and the effluent goal should be less than 0.1. And that unit's incorrect, it should be milliliters per liter. And that removal efficiency is typically 99%. So for your TKN, which is your ammonia plus your organic nitrogen, you might come in at 30 milligrams per liter, and you want to have less than 10 milligrams per liter, or a 66.67% removal efficiency. And then phosphorus you might see as like 2 milligrams per liter and less than 1, so about 50% removal, unless it's a specialized plant that's designed to remove phosphorus. So the equation for removal efficiency, and that's given as a percentage, is going to be the concentration of your influent of the given constituent and the concentrate minus the concentration of the effluent, and you divide that by the influent concentration and you multiply it by 100%. So we'll go ahead and I'll walk you through this guy's problem because it's simple, and then we'll go ahead and have you guys try one out as well. So this problem is that the average influent BOD of a wastewater treatment plant that utilizes aeration basins as their biological processes is 321 milligrams per liter, and the effluent is 26 milligrams per liter. What is the removal efficiency of this plant? So again, same strategy. First is we identify our givens, and then we identify our needed formulas. So our givens are the concentration in and the concentration of the effluent. So we have, and then we're trying to find our removal efficiency. And then we already have our formula provided to us. So then what we're gonna do is we're gonna set it up and plug in our given. So we have 321 milligrams per liter minus 26 milligrams per liter over 321 milligrams per liter. And then we multiply this by 100%. Then we're just going to cancel our units, which is the milligrams per liter. So that becomes unitless. 295 is what 321 minus 26 is equal to. And then we just divide that 295 by 321 and we multiply it by 100%. So this results in an answer of 91.9%, which makes sense if you remember from our previous slide. Between 90 and 90% is the desired efficiency for removal. And we fall right within that. So now we're going to practice this problem with you guys. So this one states the operators of the same wastewater treatment plant with an effluent BOD of 321 milligrams per liter would like to increase their removal efficiency of to 99%. What would the required effluent BOD need to meet this goal? So I went ahead and left you guys the equation, and then you're going to want to go ahead and solve it, and we'll give you guys about a minute or so, and then we'll put up the poll question. All right, let's put up the question and see how everyone did. So again, what would the required effluent BOD need to meet this goal? And the possible answers are 320 milligrams per liter, 32 milligrams per liter, 0.32 milligrams per liter, and 3.2 milligrams per liter.
I'm sorry, I did not mean to close that poll. About 54% responded, and I unfortunately cannot relaunch it, but there were the answers, so apologies, AJ.
No problem. So if everyone just wants to keep following along, if you didn't quite get an answer, not a big deal. So let's say most of us got the correct answer, 3.2 milligrams per liter. There's no real difference on all these answers except that there are different magnitudes. So if you might have multiplied something incorrectly, that's why you might have got one of the other ones. So let's go ahead and walk through the problem. So the first thing we're going to do is we got to rearrange the problem mathematically. If you notice from this one, we've moved most of our terms to the other side. So the first thing you do is you multiply removal efficiency by the influent and you divide it by 100%. And then you subtract that term from your concentration influent. And that will, once we plug in our givens of 321 milligrams per liter and our removal efficiency, we get 3.21 milligrams per liter. So next we're going to talk about biochemical oxygen demand and some simple math that's involved with that. We introduced some of those loading problems earlier. You'll see those. But then also you might be given some analysis information about BOD samples and asked to solve for that. So biological oxygen demand is important because it's the amount of oxygen consumed by wastewater and its impact on receiving waters. It's typically referred to as the strength of wastewater. What happens is microorganisms in the wastewater and receiving water consume organics, non-organics, and other microorganisms, and that process uses the dissolved oxygen in the water. Excessive BOD increases the effects of eutrophication, and the two are closely related. If you're unfamiliar, eutrophication is a process where excessive nutrients cause algal blooms, which is a large amount of algae which grow, and they consume all the nutrients and oxygen in the water, and as they die off, microorganisms consume the organic material and use up the rest of the dissolved oxygen in the water, which results in dying off of the rest of the surrounding wildlife, which don't have any dissolved oxygen. So typically how we test for BOD is we perform a BOD5 test. And this is becoming kind of archaic, and chemical oxygen demand is used more frequently. And the industry is always looking for something faster because 5 days is hard to respond to your wastewater. But the way this analysis works is that a sample of wastewater is taken for 300 milliliters, and it is left to incubate at 20 degrees Celsius for 5 days, and the amount of oxygen that's consumed is measured by calculating the difference between the OT at the beginning of the test and after 5 days. Also, the bottle of the sample is typically seeded with nutrients such as nitrogen, phosphorus, and potassium, so microorganisms can grow and thrive in there and consume as much oxygen as they would in the real world. So here's a quick sample problem. So a standard sample of wastewater used for a 5-day 20 degrees Celsius BOD test results in 84.5 milligrams of oxygen consumed. Then the question is, what is the BOD of this wastewater? Now these problems are straightforward because they're just a concentration. So you just divide the mass of the oxygen consumed by the volume of the sample volume. And so for this, we just plug in the 84.5 milligrams, and then we convert the 300 milliliters to liters, and that gives us 282 milligrams per liter. So this will be our last practice problem. So we're going to do one just like this. If you need to, I didn't put the equation on here, so if you want to write this down real quick, I'll give you guys about 10 seconds, and then we'll do the practice problem. Okay, so here's the practice problem. So it's the same thing, a standard sample, 300 milliliters of wastewater is used for a 5-day, 20 degrees Celsius BOD test, and it results in 67.8 milligrams of oxygen consumed. And the question is just like the last one, what is the BOD of this wastewater? So we'll give you guys about a minute to solve this, and then we'll put up the poll question. All right, let's go ahead and throw up the poll question and see how everyone does. Okay, so the possible answers for what is the BOD of this wastewater are 750 milligrams per liter, 226 milligrams per liter, 2 milligrams per liter, or 67.8 milligrams per liter.
The poll in 3, 2, 1.
All right, so again, it looks like most of us got this correct. I'll go ahead and show you the answer to the problem. Again, it's pretty simple. We're just dividing 67.8 milligrams divided by 0.3 liters, and that results in 226 milligrams per liter. Some possible errors could have been if you just put down 67.8 as milligrams per liter, or if you, instead of dividing by 0.3, you multiply by 0.3. Yes, so that's the last practice problem and the end of our webinar. James, were there any chat questions that came up?
Yeah, we actually have a couple. I'm going to address them in a slightly different order than they came in. One was about whether a recording of this would be available, and we will be posting the recording of this webinar on the EFCN network site in a week or two. There was a question about the Weir overflow, question about whether the answer should have been 8337 gallons per day per foot or 8340.9, which I answered in the chat, but basically the issue there was how you calculated pi, whether you use the actual value for pi 3.14 or 3.149. But there was a related question to that, asking about, in a situation like that, if you got a number that was higher than capacity, whether you would actually want to round down. And I think the answer to that would be no. Like if the unrounded number was above a value that you were trying to meet, would you typically round down there, or would you sort of assume that you were over capacity?
Well, you might, in that situation, you might want to double check your math, because if it's outside design parameters, you're going to want to think, okay, is this correct? Would they do that? And then, go in and double check your math. If you still get the same thing, it's probably best to just select the value that's going to be closest to what you got.
Right, and that's actually a good point, because in the test, they sort of account for the fact that people are going to calculate these things differently. So you might not have an answer that's exactly what you came out with, but they're, assuming you did the math right, there should be an answer that's very close, and that's what you would pick.
Exactly.
We had a question about whether solids loading rates should be in pounds per feet squared per day. I think that might have been in reference to a typo. That was from Frank. Frank, if you want to chime in on the chat, if we're looking at the right slide there.
Let's see. Are we getting any stuff on that? Because this should be, if you'll notice, you know, our solids applied is the same as like a typical loading. So it's pounds per day. And then you divide that by surface area. So it should be our pounds per day per foot squared. Because it's based on the surface area of a clarifier.
All right, and then our last question had to do with the one of the first problems where we had the TSS TDS issue, and there was a question about the conversion there, and specifically related to that, you know, turning parts per million into 10 to the negative 6. So.
Yeah, so whenever you have like milligrams per liter multiplied times, you know, the million gallons per day, it cancels out the million because it should be 1 over M, like we had kind of talked about. 1 over large M, or 1 over 10 to the 6, or just ppm.
And I think you showed that in the next slide, or the slide there after that conversion of the.
Yes.
Yeah, there we go.
And it should have 1 over 10
turning that milligrams per liter into 1 over million. So
yeah, 1 over 10 to the 6th.
Right. I believe that that's it for questions. We are fairly significantly over time. We will go through the chat after this, and if there's anything that's unanswered, we'll reach out via email because we have all your email addresses. So I think we're good to go. AJ, thank you very much.
Yeah, no one has any more questions. Thanks for your time, everyone.
Great, and I did drop this into the chat. We will be emailing the slides and recording to everybody following today's session. There will also be an evaluation that will automatically pop up, so please answer that and let us know your thoughts on today's session. And yeah, AJ and James' contact information is here on the screen if you have any follow-up questions. Yeah, have a wonderful day. And AJ, do you have any final thoughts? Though I think you already mentioned them if you did.
No, yeah, I just appreciate everyone for their time. If you have any questions, you guys can contact us. Also check out our educational videos. They have some supplementary material in there. If you have any questions about the other problems, or if you see any errors, feel free to reach out.
And we'll be back next week with a session on safety regs and OSHA. So hope to see you then.
Great, thank you so much. And yeah, we hope to see you there. So have a wonderful rest of your day.